Hello everyone, my name is Ayush and welcome back to the Funtastic Academy. Today's episode, we are going to be learning about a totally new area of theoretical computer science. We'll be moving away from sorting algorithms and start discussing about data structures. What are data structures? Simply put, they are methods of structuring your information in a way that makes it easy to access and perform operations on them. In the last couple episodes, we already learned about one data structure, the heap, used to perform heap sort. Today, we'll learn about a new one, perhaps the simplest data structure there is, the stack. We'll learn how to visualize stacks, how they're useful, and solve an actual problem with them. But before we continue, let's answer the quiz question from last episode. Ahem. In what algorithm to find shortest paths is a heap data structure used? The answer is, drumroll please, Dijkstra's algorithm. This shows how some data structures might be useful for solving different problems. So without further ado, let's start learning about the stack data structure. Let's pass the mic over to Computer Ayush. Thanks for that, Camera Ayush. Now it's me here, Computer Ayush, here to explain the concept of the stack data structure. But before we get to the stack, let's think about what a data structure actually is. Quite simply put, a data structure is simply a way of arranging your data or information in such a way that can be easily manipulated. What do I mean by that? Well, think about how in the last classes we discussed about heaps. A heap is one example of a data structure. Here we have numbers and we could put them in a simple list if we wanted to. Instead, we arrange a heap of them in this tree-like structure. And we do this for one reason. We can easily find the maximum element of the heap at any time. So we structure the data so we can do a specific manipulation on it, finding the maximum quickly and efficiently. Data structures can be designed to work with all sorts of complex manipulations. But today, we are going to learn about what is perhaps the simplest data structure that there is, the stack. You can think of a stack like a stack of plates in a restaurant. When you have a stack of plates, what are the two things you can do with it? You can either take some plates from the top of it or put some more plates on the top of the stack. Similarly, a computer science stack is a bunch of data blocks arranged on top of each other. Now, just like a plate stack, it's inconvenient for you to touch the plates at the very bottom. You can only work at the top of the stack. And the two most basic fundamental things that you can do is remove the top element of the stack or add another plate to the top. Here we represent these operations with the terms push and pop. We have a stack which is the ordered list of elements. The push operation takes in an element and adds it to the top of the list. The pop operation just returns what was the top element of the stack and removes it from the stack forever. Using these two operations, you can do anything you want in a stack. So, what is a stack actually used for? It seems really simple, but can you see what the real operation of it is? Well, because stacks have to manipulate everything at the top before going to the bottom, stacks are very useful for recursive ideas, things inside other things inside other things. You can be dealing with the bottom plates and then while dealing with them, you may have to add another plate at the top. You then deal with the plate in top inside before you get back into dealing with the bottom plate again. So stacks are really useful for anything that involves recursion or recursive applications. One really common example of this is the example of calling functions, which in your computer utilizes something called a call stack. See, when you call a function and that function ends, you have to keep track of what was the last function that you called so that you can return to the previous function. But this becomes complicated because you might have functions calling other functions, and so on. The solution is to implement functions in a stack. You start at the bottom with your main function. You keep the address of where you are in that first function. If you need to call another function in there, you store the address of where you are and then push the new address onto the stack. Meanwhile, if you return from a function, you pop that address off and then go to the address that was in the previous spot of the function. So in a large recursive program, you might end up pushing many blocks onto the stack, calling tons of functions until you solve the problem. At that point, you'll start popping and returning from everything until you reach the main case and you can return an answer. That was a nice example in theory, but can we see some actual code and maybe another example, a more practical one that you can actually understand? Yes, we will. Let's introduce the problem of postfix notation solving. The problem given to us is a relatively common one. You have some mathematical expression consisting of addition, subtraction, and multiplication, and you just have to evaluate it, calculate the answer of this expression. This is easy, right? Our programming languages already know how to add, subtract, and multiply. But the issue here is figuring out the order of operations. See, adding some parentheses completely changes the meaning of this expression. And plus, we have to keep track of the fact that multiplication has a higher precedence than addition and subtraction. You have to do multiplication first. So to make this problem easier, what we commonly do is we rewrite this system into another form called the postfix expression. In postfix, instead of writing something like 1 plus 1, where the operation is between the two numbers we are operating on, you would write 1, 1 plus. The top answer that we usually use is something called infix, where the expression is in the operands. Postfix, our operation comes post the operands. So how about we rewrite what we have here in terms of postfix? Well, we would have 1, 2 minus to indicate the highest precedence operation, the parentheses is 1 minus 2. The next thing we'll have to do is multiply that by 5. Finally, we add 1. We add 1 plus at the end. Notice that here we've removed any parentheses from our original formula. We don't need any parentheses in the postfix format. That's what makes it so cool. Any formula that you can write an infix with parentheses can be written in postfix without them. This is what makes postfix really convenient to evaluate. You can just read it from left to right and evaluate it. But how exactly do you evaluate it? We still need to keep track of where each operator comes. We need to know that this minus is operating on the 1 and the 2. instead of the 2 and the 5. How do we do this? The answer is with a stack. Look at this simple program here. It might seem large, but once you understand what's in it, it becomes quite simple. We declare a new stack S, and we're not too bothered about how a stack is actually implemented at the lowest level in memory. We just declare that we have a stack S. We also declare this function called getToken. Again, we're not too bothered about how exactly a get token works. We assume that get token returns the next thing, the next word in our equation. It could either return a number like 1 or 2, or a sign, minus sign, a times sign, or a plus sign. All that matters is that if we know the order of what symbols come when, we can evaluate it. So here's the process. We take t as the next token that is get, and we encase this in a while loop. If t is false or doesn't exist, then we skip this whole loop and we return the top result of the stack. Let's say we get a new symbol. Then what to do with it? If the symbol is not a plus sign, a minus sign, or a times sign, then it must be a number. Our symbol is a number, so we simply push the number onto the stack S dot push t, where t is a number. So you can imagine running this process on our equation here. We start with 1, which you may note is not a symbol. So what we do then is we push 1 to the top of our stack. Let's make this little stack here with 1 at the top. Now we have another number coming in, 2. So we push 2 on top of 1 at the new top. 1 is now at the bottom. Then we encounter this, a minus sign. What does this mean? Well, look in the loop. When we encounter the minus sign, we're supposed to pop the top 2 elements of our stack, and we just subtract them from one another. How does this work? Well, the subtraction operation only operates on exactly the last 2 numbers, which are the 2 numbers at the top of the stack. So we just subtract them. And now this new number might be used in a further expression. So you have to push that new number back on the top of the stack, just like it would be as if you were entering a new number. The Polish notation makes it really easy because you knew exactly how each symbol is working on the previous ones, and the stack contains the list of every previous number. Now you may notice that we're putting B first and then A. Why is that? Well, subtraction depends on the order in which you subtract. And remember, A is not the one which is on the top of the stack. A is the oldest number closer to the bottom, which was the first number written. Say the 1 in 1 minus 2. And in 1 minus 2, the 1 must come first. So we take B as the top number, A as the top number after that, popping and removing them from the stack, and we replace them by their difference, 1 minus 2, which becomes negative 1. Great. Now let's continue doing the same thing. We have a new number, 5. So we have to push 5 on the top of the stack. And we have the new symbol, multiplication. Multiplication doesn't depend on the order. We just take away 5 and minus 1 from the stack, and we produce minus 5. Finally, we take 1 to the top of the stack, and we have 1, 5. The plus operator in the postfix notation operates on the 2 numbers before it. The 2 numbers before it are 1 and minus 5, so we add them together to get minus 4. At this point, getToken returns nothing. So we exit this full while loop and return s.pop, the top number in the stack, which is minus 4. So here we've seen an example of how stacks can help us understand recursive processes like parentheses by transforming it into evaluating the things at the top before going towards the bottom. We wrote a simple routine and we understood how the pop and push functions can actually work inside a program to produce a result. We also understood call stacks, so another more common real world application used inside every computer in the world today. Now I'm going to pass the mic back to Kambayush to let us understand what we've learned today and give you the quiz question. Thanks for that, Computer Ayush. Now let's recap what we learned today. We learned what a stack is. It's a last in, first out data structure that's used for storing data like a stack of plates. We saw in what scenarios a stack can be useful, and we solved one problem for it, the postfix calculator problem using the push and pop operations on the stack. Before we leave for the next episode, where we'll talk about a new data structure, let me leave you with this one last question. What is another term for the postfix calculation structure? Tell me the answer, and I'll see you in the next episode. Bye!